Okay, we're going to be doing 14.4 tangent planes and linear approximations. We're going to see that, hey, they're really, really similar to one another. We want to kind of look back on our Calc 1 stuff. And so let me go here to the paper view. And I had a typo here, but I'll show you it and we'll get it fixed. And everything kind of jumbled up here this morning. But this curve right here is the curve y equals 2x, and it should be plus 3. I don't know what happened there on getting that typed, but that's what's graphed there. And I went through the process that we did in Calc 1 of finding the tangent line, finding the derivative to find the slope, and then using point slope formula to at this point 3, and so at this point right here 3, to find that tangent line. And I just wanted to look at that here on Desmos. So I'm going to go to computer screen view. And so there's my computer screen, and I have that graphed on Desmos there. And so if I put the tangent line on here, click it on there. Oh, I see. That's a photo of it, not a. So I have to come back on this computer screen. Too tricky when you have two computer screens and you're not used to doing that. And so right here at 3, the point 3, I'll put that point on there as well. The tangent line and the curve are really, really similar to one another. So that equation found us the tangent line. The other thing that it found us was a linear approximation. In other words, that if we zoomed in here, that there, as you zoom in, that the line, that tangent line, that linear line, and the curve are exactly the same. And you can use that linear curve for approximations. And that speeds up computing, which in some applications is really important. Computing, doing math on something that's linear. Y equals 1/3 x plus 2 is linear versus doing math for a computer. It's very quick, but slightly faster for the linear than it is for something that is a square root. And so in some applications, that's really, really important. Anyway, so that's kind of the story. And of course, we're learning in 3D. So that's kind of what we're going on. So now I have to get over my mouse onto this screen in order to go back to paper view. And we're having surfaces, and we're wanting to find a nice, the tangent plane would provide us with a nice approximation of a surface at some point on that surface, x naught, y naught, z naught. And the basic idea here, this is what we're going to kind of look on just so that you can see where the equations come from, just to get a general idea of it. Your book also goes over it. And so there's a little bit of hand waving here. But if you're trying to find the equation of a plane, well, you guys remember the two things that you need. You need to know the normal vector, a normal vector to that plane. Sorry about my voice. It's going to get better. I know it is. And you need a point on that plane. In this case, we're wanting a point on our surface. That's what we're wanting to do. And then now we're wanting to think about how we can come up with the other pieces that we need in order to, here's the knot here, in order to come up with our equation of our plane. Okay, so we had two equation builders for planes. I don't know if you remember both of them, but one of them was my favorite one to use, and that was this one, ax naught, ax, plus by plus cz equals ax naught plus by naught plus cz naught. That was the equation of the plane where, given the pieces, the two pieces that we have, do you guys remember? That was my favorite equation builder. Now, you could take this equation builder and you can subtract the ax naught, the by naught, and the c z naught. And if you do that, so I'm just subtracting all of those pieces that I said to the other side here. So if I do that, if I subtract this, and this to the other side, I get 0. And then if I give a little factor to this, factor out a b, an a out of this, a b out of this, and a c out of this, you get another equation builder for a plane. And that's the one that we're going to use right now. And so, so it's not the one I typically use, but it's one that they gave you in the book as well. And so that equation builder looks like this: ax minus x naught plus b y minus y naught plus c z minus z naught equals 0. Oops, I was writing that and I didn't have it showing. Sorry, gosh darn, that's something I might do. Now, if I rearrange this a bit, and so I want to do a little bit of a rearrange here, and so, and I'll kind of show you why here as we go. So it's just to kind of develop the idea of how you could come up with the equation of this tangent plane so that you just have an idea of where it came from, and it wasn't just boom, here's the equation. If you, after you start using it, you're like, boom, here's the equation, right? So anyway, long story short, if I divide everything by c, and then, so the c's are going to cancel out here. And then I subtract these things, 0 divided by c is 0. I subtract these two things to the other side. So that's going to leave me z minus z naught on this side. So a little bit of trickery here equals, and then I'm going to subtract this to the other side. So this is minus a over c, x minus x naught, plus b over, minus, sorry, just checking you, minus b over c. My ears just popped in. That did feel very nice. So we have that. And so now what we're going to look at and just think about here, and I tried to use this picture that came from the book, and because it's in 2 dimensions, it doesn't show it very well. So I just want to show you kind of what is going to happen here with my surface. So I'm going to bring my surface under here, and I'm going to back out a little bit. I'm going to move my paper so that it's white underneath and not that color. I had this crazy surface. Maybe I should show it to you on the person view. So my crazy surface on the person view. It's see-through so that you can see through it, but it's some kind of a surface. And there's a few points on this surface. There's one here and there's one here. Well, there's infinitely many points, but they've designed some out. And so, there goes my phone, quack, quack. Okay, so I'm going back to paper view, and I have this surface. I'm going to be interested in this one right here. And so here I kind of am going to say that my table where the white paper is where z is 0, and that going into my table downward is z is negative, and going straight up is z is positive, so that I can say the height of this point from the tabletop, the height of the point from the tabletop, so you can kind of see, is my z value. And then what I'm going to do here, and I'm going to say that right here is my y-axis, and right here is my x-axis, so that we can kind of just look at this thing. And if I was to come here and lay what I could find in my house, looking through, these came from Christmas. They're pipe cleaners that were for Christmas for a project that we did for some kids. Anyway, and I'm laying this here, this curve on here. Okay. So I just laid that curve on there. Now that curve on there, I can find the slope of this curve at every point. Um, and um, and so and I can certainly find the slope of the curve at that point. And I want to show you something about that. And so if I come here and I say to you, when, and I need to zoom in so that you can see, okay, when y is equal to y naught, okay, that's going to get this piece and drop it out. Then we will have z minus z naught equals minus a over c x minus x naught when this piece drops out. And I don't know if you guys recognize that, but that's point slope form. When you found the equation of a tangent line, right? When you find the equation of a line, we learned it with y minus y naught equals the slope m x minus x naught. That's how we learned it. And so, but this is now I'm just looking in the x direction is what I'm looking at. And so, and not x and y, but instead x and z is what I have going. And so this right here is the slope, the slope. That slope is representing the slope at this point right here of this curve that I have going. And so, anyway, so we have that story kind of going on. And I can do that same thing, laying a pipe cleaner on this curve, going in this direction and taping it down, and it would be curved, right? And I can say, well, I would like to find the slope of this curve at that point. And so, and that one would be when x equals x naught, and I would get z minus z naught equals, let's see, that one would be minus bc, right? When this would be 0, minus bc, y minus y naught, and this right here, slope-intercept form, would represent the slope, is what it would represent of that curve, of the curve that I didn't take the time to take down here of this curve at that particular point right there. So we kind of have that idea. And I told you there was a little bit of hand waving here about, I haven't started talking about, well, there's a plane here and a plane there, but just a basic idea. Well, okay. Then there's a tangent line. There's a tangent line that goes right through that point that is tangent to this curve right here. And I can find the slope of that tangent line. And in fact, we've already done that in the previous section. The slope of this tangent line I have in the x direction. Do you guys remember what it was? I hope you're saying partial derivative with respect to x. And it is. And would you agree that the slope at the point of the curve and the tangent line at that same point, they have the same slope. So we're going to look at that here. And I'll just not get my surface underneath here. And so they've kind of tried to draw the curves through here, but you can't hardly see them. If you go in your textbook, you can see the curves that they've drawn, just like the curve that I just drew on there. And then they've drawn the tangent line going through it. And so here's the story. The slope of T1, tangent line 1, is the partial derivative with respect to x at that point, x naught, y naught, that we were talking about. And that is equal to this, negative a over c there. And T2, the slope of tangent line 2, that would, I said if, but is what I was trying to say, is the partial with respect to y at that point. And so what this sort of will mean to us then, if we kind of go step back again, so thus, so this is where this formula is going to come from. Z minus Z naught, and this is the formula for the tangent plane, equals the slope negative a over c, but we just found out that the slope can be written, the slope is the same as the slope of this tangent line, f, partial of x here, x naught, y naught. So evaluated at that point times x minus x naught minus, and then the slope, right, which was the partial of y at the point, x naught, y naught. Oh my gosh, is it going to fit? Hope that it does with me. Y minus y naught, right? Y minus y. Almost fits. Call it good enough. We'll call it fitting. Okay, so we did a lovely job on that. And so kind of developing that formula. If you go in your book, they also develop the formula in the book, a little bit of hand waving by them as well, just to kind of make things simpler. But that's the idea, is that there's a curve on the surface and it has a slope at a point, and the tangent line has the same slope at that point, and we know how to find the slope of that tangent line. We did that, and so we can put that in here. And then we've come up with an equation of the plane. And so now we're going to practice it. And that's all I've done here, is just put the same formula that we just developed just here. So I'm just like to summarize, suppose f is continuous and has partial derivatives, an equation of the tangent plane to the surface, z equals f at x, y, at the point, right? X naught, y naught, z naught is, and then here's the equation of that tangent plane. So of course, example 1, they ask us to find the equation of the tangent plane, and they give us an elliptic paraboloid, and they give us this point 1, 1, 3. So we're going to go through and we're going to find that. So it's a matter of using our formula, right? So this right here is x naught, y naught, z naught. This is a point that's going to be on the surface and also on the tangent plane. And so that's our x naught, our y naught, and our z naught. Now, what we need to know is we need to know the slope in the x direction evaluated at x naught, y naught. And so we can certainly find that because it's the partial derivative of x. So we're going to find the partial derivative of this with respect to x. And this one's an easy one to do because when you hold y constant, then that part's just going to go to 0 when you take the derivative with respect to x. So we get f x, so the partial, equals, and I'm going to evaluate it at 1, 1. And so equals 4x. And I'm going to evaluate this at the point x is 1, and also at the point y is 1, but this equation doesn't have y in it. And so I just get 4 is what I get. And then the other thing I wanted to find is this point evaluated at our point 1, 1, right? X naught, y naught, 1, 1. And so f partial with respect to y is 2y evaluated at x is 1 and y is 1, but there's no x in here, so it could be though, but there's not. So this would be 2 when you plug in 1. So we did a lovely job on that. Then our formula, z minus z naught equals that partial evaluated at that point. I get lazy and don't want to write that whole thing. And sometimes I even write evaluated at the point just so that not to get so confusing with so many things. So evaluated at the point. So this is like my little subscript, and this is like my function evaluated, right? My partial derivative evaluated at a point, which we've already done. This whole thing was 4, right? And then we have x minus x naught plus, and then my partial evaluated at the point, which we already found. I'm going to put a parenthesis, put a box around it, was 2, right? And then y minus y naught. So this is going to be z minus 3 equals, and then this was 4 times x minus 1 plus 2y minus 1. And they typically solve it for z when they have it in the back of the book. Now I know that we did planes. I'm going to show you and just, the different forms that you can have a plane in. So if I solve this for z, would be add 3 the other side. So I get z equals 4x minus 4 plus 2y minus 2, and then plus 3. So when the dust clears, I get z equals 4x plus 2y, negative 6 plus 3 is negative 3. And so this is the equation of the plane. And when we looked at planes before, we didn't solve them for z. It was back in chapter 12. I told you that the standard form for a plane looked like this: ax plus by plus cz equals some d, right? And so what I would have said that the plane looked like is negative 4x minus 2y plus z equals negative 3. Might have even run a negative through that to make my x positive. I'm not going to worry about that. This is standard form, right, for the plane. And so this is another form of the plane, just rearranged, no big deal. And we do that all the time when we were in 2D, right? We had slope intercept form and standard form for lines. So standard form, we're not going to be able to see for a line, right? This is for a plane, but for a line was ax plus by equals c. That was standard form for a line. And then slope intercept form was y equals mx plus b. And so anyway, so different forms of the same line, you could rearrange it. Well, same thing kind of here. And I just wanted to look at what we found. And so I'm going to go on here, and I want to go to my 3D grapher here. And it was this one. So now I have it. I'm going on computer screen view. Sorry, I'm not very good at using the two screens. And I've already previously put it in, and I got to go onto the screen to manipulate it a little bit. So I put it in. They told us it was an elliptic paraboloid. And so you can see that when I did graph it here, that it is an elliptic paraboloid. I'm going to put this point, and that point should fall on my elliptic paraboloid. It kind of falls on the back, so I'm going to kind of circle this around so that you can see it there. At certain angles, when I look at it, and at certain zooms, when I zoom in on it, just because of the 3D grapher not being that good, well, they're pretty good, but sometimes it looks like my point is not on my paraboloid, but it is on my paraboloid. And then I want to put my plane that we just found, the plane that we just found on there. So there's our plane. And then the idea is that this plane just is going through that point A that we have on there, and it is just tangent to our elliptic paraboloid at that point. And so that if we were to zoom in, and I might even turn it a little bit here and start zooming in. Am I zooming in or am I zooming out? I'm zooming out. If I zoom in, that plane and that paraboloid will, just like the curve and the line, you will not be able to tell the difference between them as you zoom in. That at that point, the plane and the paraboloid are exactly the same. So anyway, so that's kind of the idea on that. While I'm still here on my computer screen, I had put down there from your textbook. So this is and I just click over onto it, and explore and test. And so I've put that on, and so they have an example here, of a different shape, but the plane that they found through it. And if I zoom out, I think it's zoomed out as far as it'll go, but if I zoom in, you can see that as you zoom in, that you're getting you're looking at a smaller surface, and smaller and smaller, until that the plane and the surface are exactly the same, for a small little bit. So that's kind of the idea of it. So I want to come back on this computer and back to paper view. Okay, so we did that. And then they talk about a linear approximations of or the tangent plane approximation. That's another name for it. And they gave you a formula of it here, and we're going to give a try to it, and see how we do. Um, so, and then there's a theorem there too. If a partial derivative, f, the partial derivative with respect to x and with respect to y near a point AB, exists near a point AB and are continuous at AB, then f is differentiable at AB. So they're asking us on this example to explain why the function is differentiable at the given point, and then do something else. So that's what we're gonna do. So what we want to look at, so that we can explain why it's differentiable, is we want to look at the partial derivatives, and so let's do that. Okay, so we have this function right here, and we want to find the partial derivatives. Can I zoom in a little bit to make it just a little bit bigger? I can. I don't know if that's good, but I'll do that. So I want to find this first partial derivative here, f x. Okay, so that's my first goal, is to find it. Now, when I'm looking at it, I'm taking the derivative with respect to x, and it's in the denominator. And so you have choices. You can use the quotient rule, or you can write this parentheses around this to the 1, and then raise it to the numerator and write it to the -1, right? And then use the chain rule. I don't care which one you did. And in class the other day, we did it both ways, just to show that it came out. And so whichever one you think is the easiest there. Me, I would probably use the quotient rule, is what I told you then. And then I notice in my notes over here that I used, I raised it to the -1, and then used the chain rule. Anyway, it doesn't matter. So I'm gonna, because I just said I probably use the quotient rule, I'm gonna do the quotient rule. It gives me variety in my life. So this is a constant, and when you take the derivative of a constant, you get 0. And then when you take the derivative of x here, you get 1. So that when I crisscross applesauce here to find this, this time I'm not wanting to find it at this point right yet. I am going to want it at that point, but right now I'm wanting to show that it's differentiable at this point. So I want the variables in there, I guess is what I'm saying. And so this would be 0 times 1 plus x, right? The quotient rule, 0 times here. So my little crisscross applesauce, and then minus this times this. So minus 1 times 1 plus y, all divided by 1 plus x squared. Hi, Ty. I'm making my video. Can I call you right back?
Sorry, yeah.
No
Bye.
problem. Bye-bye. Sorry. Um, all the people I love, right? Including you guys. And so here we're going to have here negative 1, 1 plus y over 1 plus x squared. And I want to see if this exists at near the point 1, 3, and if it is continuous near the point 1, 3. And so that's what I'm looking at here. Well, it would not exist if x was equal to negative 1. So if I was trying to be near the point negative 1, then the denominator would be 0 and it wouldn't exist. So I'm fine at the point 1, 3. There's no problem with y at all at near 3, and there's no problem with x near 1. And so it exists at 1, 3, and it is continuous in a little neighborhood around 1, 3. So it's pretty far away from 0.13 that it does not exist. So we also want to find the partial derivative with respect to y. Now, it's not as hard because this is the denominator is a constant, whereas so it's a little bit easier. So remember what you do when you're taking the derivative and your denominator is a constant, or you have a product that's a constant, it just holds still. And so 1 plus x down in the denominator, when you're taking the derivative with respect to y, is just a constant. And so you can just hold that still. So you can say fy here equals, and then with 1 plus 1 over x, I'm going to write it that way, is just hold still. And then times the derivative of the numerator. The derivative of 1 is 0, and the derivative of y is 1. So this is times 1. So the derivative, the partial with respect to y, is just, I don't know why I wrote fy. I wasn't wanting to write that. The partial with respect to y, I was wanting to write 1 over 1 plus x. And if I'm near 1, 3, again, where am I having the problem? At negative 1, and that's pretty far away from 1, 3. So it exists near the point 1, 3, and it's continuous near the point 1, 3. So I can say, since fx and fy, the partial with respect to x and the partial with respect to y, exist near 1, 3 and are continuous in a little neighborhood around 1, 3, continuous. So continuous. Then what we can say, what that leads us to say is that f is differentiable. So since both of those things are true, so f is differentiable. So in that little neighborhood near 1, 3. So differentiable at 1, 3, and so I'm going to say at 1, 3 because that's what they really say in the theorem. So, and that's what they asked us to show. So I'm going to say at 1, 3. That's what they said in the theorem. Okay. Now the other thing that they wanted us to find here, and I spent a lot of room on that, just doing that little part of it. But they wanted us to find, I'm going to zoom out a little bit. they wanted us to find, after we showed that it was differentiable, they wanted us to find this. And so they're wanting us to find L at x, y equals f at AB plus the partial evaluated at AB, x minus a plus fy evaluated at AB times y minus b. So they're wanting us to find that linearization. That's what they're asking us to find. And so we're going to give a try to that. Now our AB here is 1, 3. That's what our AB is. And so the first one thing I haven't found is I haven't found F at AB. And I'm going to, I'm kind of out of room. And so, and I wanted to put something else down here. And so I'm just going to come and just put it right here. And I'm sorry, I always do that. And I always say that I'm sorry, but our FAB, which is F of 1, 3, is equal to, sorry, put in Y is 3 and X is 1. So if you do that, that's 1 plus 3 over 1 plus 1, which is 4 over 2, which is equal to 2. So we know that what that's equal to. The other thing that we want to know is what is Fx at AB, our partial at 1, 3. So our partial at 1, 3. Now we found our partial derivative right here. And if I put in 3, so this would be equal to negative 1 times 1 plus 3 over 1 plus 2. No, what was x? It was 1. Sorry. 1. When you add 1 and 1 together, you get 2. That's what I was getting 2 on. So this becomes negative 4 over 2 squared, which is 4. So this becomes negative 4 over 4, which is equal to negative 1. So we see that right here in our formula, right here, that's equal to negative 1. We have one more thing to find, and we're going to put that right here in our formula. And so, it won't take me very much room, but I'm going to put it right here. And so Fy at that point, 1, 3, which is 1 over 1 plus 1, which is half. Okay, so we're going to have those. So we're going to put all of these things in. So we just found this up here above. It was 2. Okay, so here is our linearization. This was 2 plus this was negative 1. X minus a was 1 plus half y minus b, which was 3. And so now I'm going to have my linearization here. If I just fix it up just a little bit. So 2 minus x plus 1 plus half y minus 3 halves. When the dust clears, can you still see what I'm writing? At negative x plus half y. And then 2 and 1 is 3, minus 1.5 is positive 3.5. And they say that this would be a good approximation if we wanted to know values of our function here near when x is near 1 and 3. So, values like 1.1 and maybe 3.05. And then we could put them in here and then just have a linear way of finding them. So this would give us a good approximation of that function right there. And something that's linear takes a little bit less computing power. So that's the reason that they're telling you about it. I wanted you guys to know that this is no different than finding the tangent plane. And so, and they kind of they do remark on that in the book as well. So if you were like, I don't really want to have two formulas that find the same thing, I'll just use one formula and know that they both of them find the same thing, you definitely could do that. Now, when you found the tangent plane, what you wanted was a point on the surface. And so I just want to show you that they're exactly the same. And so this was called finding the linearization. But when we found the tangent plane, right, we wanted a point on the surface, and that point was 1, 3. We called it x naught, y naught, and that was our, that's what we called A and B there, but z naught. Well, how do you find z naught? Well, you plug those things in, and we did that, and we found 2. We found that z naught was 2. Do you guys remember when we plugged them in? We found it. And so that is a point on the tangent plane and also on the surface, is what that is. Then the other thing that you needed to know was the partial at x, y, at a, b in this case. Well, we just found that, right? The partial at the point was equal to -1. And you needed the partial with respect to y at the point, and we found that was half. And then the formula that they gave us was this: z minus z naught. I'm trying to show you that they're the same, right? Equals, and then the partial at the point, and then x minus x naught plus the partial at the point, evaluated at the point. I'm not going to write the point in here. I'll put at p. How's that? At p point, and then y minus y naught. Well, what is z naught? It's 2. Z minus 2 equals then -1 x minus our 0.1 plus, I hope you're seeing a lot of the same things going on, right? Half y minus, and so it's not a different critter, right? And so we distribute here, we get negative x plus 1 plus half y minus 3 halves. And we add 2 to the other side. So z equals add 2 to the other side. And boom, you get the same thing. Z equals. Now, when someone asks me to find a linearization as opposed to the tangent plane, this was plus 3 halves, right? It's the same arithmetic. 1 plus 2 minus 3 halves. So when someone asks me to find the tangent plane, I say z equals da da da. When they ask me to find the linearization, then instead of saying z, you say L at x, y. And so equals x plus 1/2. So you could do it the same way, I guess, is my point. Nothing, no miracle there. Okay. Just again, what we found. So I'm going to go here to my computer screen. I'm going to choose the right picture, which is this one. Go to my computer screen. So I plotted z equals 1 plus y divided by y equals 1 plus x. That's plot there. And they've put in the gray there is the x, y plane is what it is. That's when z is 0. And you can see that this is a pretty complicated, in 3 dimensions, pretty complicated graph, and pretty complicated looking. And we're interested in a point. This is going to appear on the XY plane. I put in z is 0 there, and let me see if I can flip it around so that you can see that point just on the XY plane. I'm not very good at moving it around. There it is, just on the XY plane. It's not on, that point is not on the surface that we have. But that point would project onto the surface. And so here I've clicked it. So it projects onto the surface. And so there it is, a point on the surface. And if I'm wanting to approximate points in this neighborhood, I can use this plane that goes right through there. And that plane is the tangent plane. And if I zoom in on it, that plane does a really good job of approximating points in that neighborhood. And so here I am zooming in on it, or maybe I'm zooming out. I don't know. I get confused at which way I'm going on there. And I get that back in the center. Like I said, sometimes it looks like they're not, like B has come off of it. And here it's looking like B has come off of it, but it's just the software. It hasn't. When I rotate it around, you'll see that well, I can maybe zoom back out. It's because that plane really comes over here and includes the B, and so does that surface. But in order to draw it so that it looks like it has some shape to it, it doesn't. So I wish I wasn't showing that looking like it's come off of it, because it definitely hasn't. It's just that it hasn't extended, and I've zoomed in so far that it hasn't. But anyway, that's what you found. Okay, no, you need paper view, my friend. Okay. Then the other thing, and they did this in 2 dimension 2 in the same section, they talked about differentials, is what they talked about. And what the differential gives you is it gives you an approximation of, and that approximation is called dz, of the height change between 2 points is what it is. And so what would be the height change? Now, delta z is the exact height change, is what it is. And dz is using the tangent plane to find the height change, is what it is. And it should be kind of close. dz should be use less computing power. Of course, they've given us ones that are so easy so that we could calculate both of them. And so we don't feel like that, because they want us to see that, hey, they're similar to one another. And so that they're very close to one another. So here they're asking us to find the differential here on example 3. And so they're asking us to find dz. And how you find the differential is that you find the whichever notation you want. But here's the partial with respect to x. Here's the partial evaluated at the point with respect to x. And so anyway, so that's what we're gonna go and find, and the partial with respect to y. And so we'll give a try to that. So we'll see how we do here. And so if I want to find fx here, the partial with respect to x, so that's not going to be too bad. Now y is a constant, so that's going to be 2x. I hope that you're finding it ahead of me. Plus 3x, excuse me, 3y is the constant, so write it down. And then the derivative of x, which is 1, so times 1. So this is 2x plus 3y is what that is equal to. I also want to find the partial with respect to y. So x squared is a constant, so it would be 0. X is a constant, so write it down. 3x is the constant times y, which is 1. The derivative of y is 1. So times 1 minus then y squared, right? The derivative there is minus 2y. So when you get this is 3x minus 2y. And so then dz is what they were wanting us to find, is equal to 2x plus 3y. So there we found it. Okay. Then I realized that I haven't got enough room to write. And so I had made a note to myself from last semester to move this up just a little bit. And I didn't. So please forgive me. I know that you guys will, because you guys are really sweet people. And so one of the things, because x and y are our independent variables, is that when they tell us that x changes from 2 to 2.05, then what they're telling us is the change in x. right? And the change in x is, so x is changing from 2 to 2.05. So the change in x is 0.05. And so here, x, they're telling us x is 2, and it's going to change to 2.05. So that tells us that delta x, which is exactly equal, because independent variable, to dx, is equal to 0.05. I'm going to write that right there. And then here they're saying that y changes from 3 to 2.96. And so y is 3. I'm going to write that just here, just giving myself more room. I would have wrote it underneath, but I didn't move that up. And then that tells us that delta y, because independent variable is the same as dy, is equal to, when I subtract those, I get negative 0.04, right? If you take and subtract that on your calculator. If you take 2.96 and you subtract 3, you're going to get 0.096. And they want 0.04, sorry, that's the 96 there. And they want us to compare the values of the actual value dz and what we approximated it to be. So the delta z dz. This is the actual, the real dz, the real change in z. This is the approximation for the change in z. That's very hard to say. You're probably saying, no, it's not. It's not that hard to say at all. So let's start off with finding delta z. Okay. So how you would find delta z is that you need to find z when x is equal to 2 and x is equal and y is equal to 3. So maybe I should write that right above so that you know what I'm going to do. X is 2, y is 3, and I'm going to find z, and where I'm going to go is right to this equation right here that says what z is equal to. So this is 2 squared plus 3 times 2, and then y was 3, and then minus y squared, 3 squared. So z is equal to, when you do that arithmetic here, 4, 9, 18, right? 4 plus 18. Take away 9 is 4 and 18, 22. Take away 9, is that 13? I hope 13. Okay. Now I want to do this again, and this is why I was telling you that I was short on room a little bit. But now I'm going to put it right here. X is 2.05 because that's what it changes to, and y is 2.96. So when I plug that in and do the arithmetic, I'm going to get z equals stomach growling. I told myself that I had to make this video before having breakfast. And so my stomach is absolutely growling because I'm used to having breakfast. My kid's doctor, when my kids were little, told me that if you set your alarm clock for 3 o'clock in the morning and got up and had a meal at 3 o'clock in the morning, that pretty soon your stomach would wake you up at 3 o'clock in the morning to have a meal. And he was liking this to giving our children a bottle in the middle of the night. And certainly, and then if you stop doing that, then they'll stop waking up for that food anyway. I don't know why it got me on this, but I guess I was going to say that if I stopped having breakfast in the morning and started having it a little later, maybe my stomach would handle this a little better. So now delta z is equal to, and I just want to look at the change in these two things, right? So I'm going to subtract them. 13.6449 minus, so this is what it changed to, minus what it started out, 13. So delta z, I hope you can still see this, is equal, so this is the actual change. And they wanted me to find that, and they wanted me to compare that to dz. And so here, I know, I'm sorry, dz, well, we found that right here, right? So this is 2 times x, and x was 2, plus 3 times 3, and then dz, right? dz, I'm using the formula here, which was 0.05 plus, and then 3 times 2 minus 2 times 3. Hey, that's 0, right? Because that's going to be 6 minus 6. And then dy, which was negative 0.04. So when the dust clears, I had a calculator, and was trying to do I didn't do that arithmetic in my head. I admit I cheated. I feel like I need to check it, but and you guys are saying, no, don't. But I won't be able to help myself because I'll be thinking, well, I did that earlier and I didn't do it. I didn't put it in and make sure that it was. And without you guys to check me, I make arithmetic mistakes all the time when I do my notes on my own. For one thing, I allow myself to chomp down on food when I'm doing my notes on my own. And so sometimes I make a mistake, but I didn't this time. I got the same value. So now I'm going to put this in here and get the dz. Should I allow myself to say 4 plus 9? What do you guys think? Times 0.05. And so 13 over 20, which is 0.65. This part over here was 0, so that's the reason I didn't put it in. Is it always 0? And the answer is no, it's not always 0, just in this particular problem. It was. Oh, that's a 6. Okay. So here was delta z, and here is dz, and this one is the actual change in the height, and this one is approximating that change in height. And you can see that this is a 6 here, if you were thinking it's not, that, hey, they're pretty close to one another. Of course, you use this on ones that you couldn't easily do this. That's when you do this. So they have given us one that was easy enough that we could find both so that we could see that they were similar to one another. But when you would approximate it was when it would be too difficult to calculate. That one would take too much computing power to calculate it. Okay. And so one last page and then breakfast for me. And anyway, so let's see what we have here and how it goes. So it says a cylinder soda can, I'm sure it was Coke and not Pepsi, is being constructed with a height of 11 centimeters and a radius of 3 centimeters. If the height has a possible maximum error of 0.1 centimeters and the radius has a maximum error of 0.2 centimeters, what is the possible error in the volume? So what we kind of have to think about is what is the volume of a cylinder? And that volume is pi r squared h, if you didn't remember it. And so if I want to think about the partial derivatives, right? Because I'm kind of building on, this is my z, and my r is like my x, and my h is like my y, and I'm wanting to come up with, what I'm wanting to come up with is dv, is what I'm wanting to come up with. And so, should I write what I'm wanting to come up with? I'm wanting to come up with, so that I could estimate that error, dv is what I'm wanting to come up with. And so let's think about what that would be. It would be the partial with respect to r times dr, right? Plus the partial with respect to h times dh. That's what I'm wanting to come up with, because I'm wanting to find the little bit of error in the change in the volume, right? Is what I'm wanting to find. What is the possible error in the volume? So what is the change in the volume from what we wanted it to be to what it is? And so let's find this first. And so if we try to find that, then it's going to be, so partial with respect to r. Now pi is a constant and h is a constant, so I'm going to hold them still. And then take the derivative of r, so that's 2r. So this fr right here is equal to 2 pi rh. Is that okay? And so we did a lovely job at that. Now we want to find those at our point. We want to find that at our point, right? And our point is when r is 3 centimeters and when h is 11 centimeters. So at the point, this is fr at the point. I'm going to put parentheses for our point. This is 2 pi r, which is 3 centimeters. H is 11 centimeters. And this is equal to, I need a calculator, I'm going to leave pi in it. 2 times 3 times 11 is 66 pi centimeters squared there. Then I want to also find f h, the partial with respect to h. So h is now a constant, so the other part holds still, pi r squared, times the derivative of h, which is 1. So this is what this is equal to, the partial with respect to h. And I'm going to plug in my point because I want to find it at the point. I probably should have said this is at the point, right? We knew that, but I didn't. Now I'm getting this in my way. You're like, don't erase. Leave it there. It's okay. And I'm like, no, I gotta fix it a little bit. My point times dr plus at my point times the h. So right here, I'm finding dh at my point, which is when r is 3, so that's pi times 3 centimeters squared, which is 9 pi centimeters squared. Okay, so now the change in my volume, the estimated change in my volume is going to be right here, 66 pi centimeters squared times, now dr is the same as delta r, which is the maximum possible error in my radius, which was, this was the height, 0.01, and the radius, the error could be 0.2. So this is equal to 0.2. I think that's quite a bit of error. 0.2 centimeters plus, this is my point, right there, 9 pi centimeters squared. And then dh, that's the dh in my writing where you can see dh is the same as delta h, which was given to be 0.1. Those are the independent variables, right? So 0.1 centimeters. And so when the dust clears here, I'm not going to put the pi in because there's pi on both of them, but 66 times 0.2 plus 9 times 0.1 is 141 over 10 pi centimeters cubed, Stevie. That would be the exact value, right? And this is an approximation, so I'm going to go ahead and do, well, that's not this is an approximation given an exact value, right? But because it's approximation, I'm going to put little squiggly equals. I'm going to times this by pi on my calculator. My son admitted to me that he has used as an engineer pi to be 3 before. I couldn't believe it. I love him, but it's hard. And so this is 44. I'm going to go to the 10th, 0.3 centimeters cubed. And so that's quite a bit of volume. And that is volume, right? Centimeters cubed is volume. So that's quite a bit of volume to be more or less in a can of soda, right? Seems like an awful lot. And so I decided that I had to figure out what that was as a percentage. And so if you're interested what it is as a percentage of the change, of the from the actual, right? So the volume of the actual soda, if it's made exactly perfectly, would be volume equals pi times the radius was supposed to be 3 centimeters squared, and the height was supposed to be 11 centimeters. And this would be, if the can was made perfectly, right? The volume would be, that's 9 times 11 is 99 pi centimeters cubed, which is 99 times pi, 3.11 point, point 0 if I round to the 10th. But the percent change would be the change in the volume divided by the original volume, or what the volume is supposed to be. Original volume times 100%, right? And so the change in the volume is 44.3. The original volume should be 311. And this is in centimeters cubed. And this is in centimeters cubed. So they're going to go away. And that's just going to be something that is a percent. And when I did that on my calculator and figured out what that was going to be, 3 times 100%, like 14% more in this can that was made a slightly bigger, like, at the most. And that's a lot. That seems like a lot. This problem was made up by one of my colleagues, so I'm not sure if if the numbers are what they are, because what I started asking is, okay, if that's the case, then how can I go to Costco and find the can of sodas that are slightly bigger on the shelf so that I can get 14% more? Anyway, it's silly. So anyway, but a little example. Oh, this example, it came from one of my colleagues, but it might have been in the book too. Anyway, okay, I'm done with this video and I've got to get myself ready for my day. You got to get yourself ready for your day. Maybe you're in the middle of the night. I'm not sure. I hope your day is going good though. And bye.